Okay, so yes, I have basically scheduled the entire time to work through this. Make sure it's one of those deals that if you don't have a good solid foundation, then there's no point in going on, okay? So don't flip out if you're going, man, I am so screwed, okay? It'll be fine, okay? I get it, and this is why I said, because you all come from such divergent backgrounds in terms of like, when was the last time you took Chem 2, and, you know, God, I've forgotten everything, and so that's why I'm just saying, I'm assuming that you all don't remember anything, and we're just going to basically start from scratch, too simple. Okay, so let's even start with, for example, you know, your aluminum chloride, that first one. So you have aluminum chloride, come on, which should be AlCl3, okay? Now, let's talk about why this is what it is, right? So, if you look at the structure of aluminum, so what's the atomic number of aluminum? 13, right? So in this chunky, weird, extremely high density nucleus, you've got 13 positively charged particles which don't want to be there. Okay, they don't want anything to do with each other because they're all positive charges. So to kind of balance and mediate that, there's some neutrons in there. So now, what's the relative atomic mass of aluminum? 27? 26.99, right?
Yeah.
Okay, so we're going to round that at 27.0. Okay? So when you're doing relative atomic mass calculations, at least go out to the nearest tenth. If you're going to go to the hundredths, that's fine, but you don't have to go out to like the 10,000th place, okay? Because our scales aren't going to measure out that far. So when you're doing relative atomic mass, at least go to the 10th. If you really want to be hardcore, you can go to the hundreds. So let's talk about this whole concept of relative atomic mass from a historical perspective. When you look at how Mendeleev first laid out the periodic table, which is in the 1800s, they had no concept of electrons, protons, neutrons. Even if you look at a chemistry book from 100 years ago, if you look in the index and try and find the words electrons, protons, and neutrons, they did not exist, okay? It wasn't until like the early 1920s that we actually figured out that there were smaller subatomic particles. Because the word atom comes from the Greek word atomist, which means indivisible. So in the traditional thought process of when they were talking about atoms up to the early 1920s, here was the thought process that they had. They said, okay, imagine that you have a piece of gold, okay? And you have this infinitely sharp knife. And you could take that infinitely sharp knife and you could take that block of gold and you could cut it in half. Well, that knife is only going to go in that path of least resistance. It's only going to go in between the particles where it's going to go. And then you're going to take that half of that gold and then you're going to cut that in half. And you're going to keep cutting this gold smaller and smaller and smaller and smaller and smaller. And at some point, you're going to reach a point that when you try and cut that last tiny bit, you can't cut it because at that point there's no empty space. So one of the great quotes of science is that the only thing that exists is matter and empty space. Everything else is just opinion. And so that comes from that Greek philosophy that says, you know, when you cut this thing, it becomes smaller and smaller and smaller and smaller and smaller. And you reach that point where you cannot divide it anymore. That comes from the Greek word atom, which means indivisible. So up until the 1920s, their view of the atom was that it was like basically almost like a tiny Lego block. And if you take those Lego blocks and you arrange them in one situation, you get Oreo cookies. You arrange them in another way, you get squirrels. Okay? If you put them in another way, you get paint. Okay? Whatever. So it's just how you arrange the little Lego blocks. And that was cool. So if you look at John Dalton's atomic theory, and he was the first one that came up with like a true atomic theory. He said, okay, atoms are combined in whole number ratios, which was cool, which is why water is H2O, or why aluminum is AlCl3. It's not AlCl3.5. It isn't water H3/4O, okay? And that reinforced this idea that these were tiny, tiny little Lego blocks, right? So that was cool. He also said that all atoms of the same element are identical, because at the time, they didn't have the capacity to measure the different masses based upon isotopes. We didn't have that capacity. We didn't have the good enough technology. So they said, hey, all nitrogen atoms are the same, all oxygen atoms are the same, all carbon atoms are the same, because they didn't have the capacity to measure isotopic masses, because we didn't have the instruments at the time. So there were some aspects that were right, but the main thing that he got wrong was he said atoms were indivisible. But at the time, it seemed logical. And they said, well, this is why they combine in whole number ratios. So in the early 1920s, 1910, 1920s, scientific community in the world was actually almost like depressed. Okay? It was a bad time in the scientific community in the early 1900s, because they thought they were out of jobs. Literally, if you read the writings at that time, they said, we don't have anything left to do. They had gravity figured out because of Newton's laws of motion. They could predict the motions of the planets. They had that figured out. They had the atomic theory figured out. Okay, or they combined in whole number ratios. They thought they had that done. Physics was, okay, you have friction, boom, there you go, gravity, all right, cool. And so literally they thought, the only thing we have left to do is to tweak the constants. Maybe Avogadro's number isn't 6.02 times 10 to the 23rd, maybe it's 6.04. Okay? And they were depressed because they were literally thinking, we've worked ourselves out of a job, because they thought they had all of the major scientific ideas figured out. And of course, this is my bias, but the physics department screwed everything up. Because the chemistry department was cool because they were trying to figure out the best way to purify cocaine, because at the time you could buy cocaine over the counter. And they were happy doing that, and it was like, cool, all right, nice. And so, but the physicists were going, we're looking for a job. So it gave the physicists the job of trying to figure out, okay, well, what's matter actually made of? So the great story of how physicists approach things is that fundamentally physicists like to smash things together. So when you look at like the history of the atom, all of the major breakthroughs came from the physics department, not from the chemistry department. So the great story is that, okay, you have a Volkswagen Bug and you want to figure out what the Volkswagen Bug is made of. You slam it into a wall at 10 miles an hour. Oh, okay, great. A little bit of a bumper fell off. Okay, well, let's get it up to 100 miles an hour. Okay, well, great. Now there's broken glass. Get it up to 1,000 miles per hour. Oh, look, there's an engine inside. Okay, cool. What's the engine made of? I don't know. Get that thing up to like 10,000 miles an hour and slam it into another engine. Oh, there's a piston inside. What's a piston made of? I don't know. Let's get it up to like, the speed of light and slam it into another piston and see what's going on. And that's basically how we figured out the structure of the matter. And that's what we still do. Particle accelerators are based upon that idea. We smash things together and we see what flies off. Okay? It's crude, but it works. So when Dalton had his atomic theory, they said, hey, it's indivisible. First thing, J.J. Thomson discovered the electron. So that was the first shot across the bow. You figured out that there were these small negatively charged particles. Well, that created a whole problem, because we couldn't be here if the universe only was made of negatively charged particles. Because that's what I showed you yesterday with the balloon and the piece of plastic. If everything in the universe was negatively charged particles, we wouldn't be here having this discussion. If everything was positively charged, we wouldn't be here having this discussion. If everything was just neutral, we wouldn't be here having this discussion, because the atoms would never combine together. So there's this balance of negatively and positively charged. That's what allows us to exist, is because these oppositely charged particles form bonds. So then it's like, okay, Rutherford comes along, he shoots the alpha particles at the gold foil, most of the particles go straight through, 1 in every million would hit and bounce back. So that would be like me taking this baseball and throwing it at that wall, and I do it 1,000,000 times. 999,999 times, the baseball goes through the wall. Well, 1 in 1,000,000, that baseball is going to hit and it's going to come back to me. So that would lead me to conclude that that wall, even though it looks solid, is actually mostly empty space. But if I hit it just right, there's one little piece is going to hit and it's going to bounce back. Because here's the challenge. There's about 94,000 atoms stacked end to end across this piece of aluminum. So imagine that you're shooting another atom equally small, and you're going to try and hit this edge. So not only are you going to try and hit that edge, you're going to try and hit one of those 94,000 atoms that are within that. And not only are you trying to hit that atom, you're trying to hit that tiny dot of matter that's in the inside of that atom in the nucleus. Because that's why it says, oh, it's like splitting the atom. Well, splitting the atom is really, really tough to do because those 13 protons in that aluminum atom are held very, 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 very tightly together. And that's why when I came in this morning, I didn't worry about that aluminum changing into something else. I knew this was still going to be aluminum, okay? Stable. That's one of the things that we had to overcome. How do you explain the stability? And that's how this, oh, okay, right, we have this dense nucleus. They're held together very, very tightly. And then you got these electrons like the chihuahuas of the atomic world, and they're orbiting around here going, hi, woo, I'm an electron, woo, I'm hyper, okay? And they're bouncing around. And we really don't know where they are, and that's okay, we don't care, okay? We don't know. We can talk about regions of probability. Oh, they're most likely within certain regions. So when they arranged the periodic table initially, they arranged it based upon the chemical properties that they knew, and they also based it upon a repeating pattern of relative atomic mass, because they knew relative atomic mass. They didn't know the actual mass, but it was a relative atomic mass. It'd be like, okay, in this class, we're going to have a relative atomic mass, and we're going to assign Zach as a relative atomic mass of 2. Okay, it's arbitrary. We're just going to define Zach's mass as 2, okay? So let's say my mass is twice that of Zach's, okay? So my mass then would have a relative value of 4 because I have twice the mass of Zach. I don't know what his mass is. I don't know what mine is. I just know that relatively my mass is twice as much. And that's what they did. They said, okay, we're going to set hydrogen as a relative atomic mass of 1. It's a simple number. Boom, we're going to call that 1. But then they looked at carbon. They said, carbon, if you stack up 12 hydrogen atoms, that has the mass of 1 carbon atom. Okay, so that means relative atomic mass of carbon is 12 because it's 12 times as massive as hydrogen is. We don't know the actual numbers, but it's a relative kind of thing. Magnesium's relative atomic mass is 24.3. So that means a magnesium atom is about twice as massive as a carbon atom is. So, again, to really understand this, you have to know that they did not know the actual masses of the atoms. They didn't have the capacity. All they knew was relative mass, okay? And so they arranged the periodic table based upon repeating chemical properties and relative atomic mass. Okay, that's all they had. They didn't know atomic number. They had no concept of electrons. They didn't know anything about S, P, D, and F sublevels. They had no knowledge of that. But it worked. It worked beautifully. And so one of the beautiful things that Mendeleev did is he actually left gaps in his periodic table. He says, I'm predicting that there's going to be some elements here that are going to fill this, and we don't know what they are yet, but I'm going to make a prediction that there's some gaps here, and we're eventually going to find them, and they eventually did. Okay, like aluminum was one of those that filled in that gap. So when you look at aluminum, you've got 13 protons, okay, and that's the defining thing, is the 13 protons. That tells us what this is going to be. And then around here, you've got 13 electrons, okay? And again, Mother Nature is a lazy prima donna. Mother Nature is only going to do what is easiest for Mother Nature to do. So Mother Nature sits here and goes, man, I got 13 electrons out there. So if you look at that arrangement, that's 1s2, 2s2, 2p6, 3s2, 3p1, okay? If you're into Lewis dot structures, you're going to put aluminum, and that's going to have 3 dots around that structure, okay? And if you don't know what that is, look on your periodic table. Elements starting with lithium have 1 dot. They have 1 valence electrons. Beryllium, that column has 2. Aluminum has 3. Boron has 4. And you can go across like that. You don't have to know the structure. You just have to figure out the pattern. Oh, you get over to the halogens. Halogens have 7 dots. They have 7 goats. They want 8 goats. Oh, they're going to bring in a goat. Oh, teacher, I will go get a goat for you. Cool, go get me a goat. Okay, go get a goat. Now I have 8. Now I'm happy. Okay, but if I only have 1 goat, it's like I could care less about the 1 goat. Goats are a pain. I could care less. Take the goat. Don't care. Okay, and that's basically what Mother Nature does. Is it easier to gain goats or lose goats, or is it easier to share goats? Because then you get into carbon. Carbon has an identity crisis because carbon has 4 goats. It's like carbon sitting there going, God, I don't know what to do. Do I lose 4 goats? Do I gain 4? I don't know. I'm conflicted. So carbon just says, carbon is this kind of this kumbaya, Peace Corps, hey, hippie kind of thing. And carbon says, I'm not really into taking electrons. I'm really not give up 4 either. I'll just share my electrons. So carbon tends to form covalent bonds because it doesn't have enough ability to take in 4 goats from somebody else, but it doesn't want to give up the 4 goats that it has. So it goes, let's just do a timeshare. Okay? So carbon tends to share electrons. That's why carbon doesn't form ions. So aluminum sits here and it goes, I got 3 valence electrons. But we don't want them because I'm going to become more stable if I can get rid of them, because then I can look like a noble gas of neon. So aluminum makes this decision. It goes, I can either gain 5 goats or I can lose 3. Aluminum goes, screw it, I'm getting rid of the 3 goats. But we don't like them anyway, they smell bad. You're out of here, okay? So aluminum gets rid of those 3 goats. It still has the 13 protons. So now chlorine sits here and chlorine goes, wow, this is cool. Chlorine is a halogen. It has 7 valence electrons. That's cool. It has 7 goats. It wants 1 more. So chlorine comes up and says, hey, dude, I'll take 1 of your goats, but it can only take 1 goat. Can't take all 3. It can only take 1 goat because it only wants to end up with 8 because of the law of octets. So then aluminum goes, hey, whoa, I still got 2 more goats to get rid of. So another chlorine comes along and says, hey, I'll take 1 of those. That's cool. Another chlorine comes along and says, whoa, I'll take another one. So that's why it's AlCl3, because you're going to have 3 people taking the goats. There you go. That's it. That's why it's AlCl3. But it can't be AlCl4. Okay? Now, it can't be that because then the oxidation numbers don't add up to equal to 0. So that's why your ionic compounds can only have 1 possible ratio, because the oxidation numbers have to add up to equal to 0. Okay? Skippy, what are you doing? You have been in my room for less than 20 minutes and you've already annoyed me more than anyone else has.
My bad.
This is, Skippy, this is why I... okay.
It's about 182 molars off on this one.
Okay. Skippy and I have a love-hate relationship. Okay, I taught Zach last year, so this is you all are walking into a love-hate relationship that has been around for quite a while. Heavy on the hate, light on the love. Okay.
It's not 183 molars.
I told you I was off by about 182.
Oh my God, Zach.
I think my head's
Okay.
I was off by 182.
Okay. Now, so when you get into the naming them, when you name them, some elements, especially in that transition block, have an identity crisis. They can't figure out what they want their oxidation numbers to be. So when you look at, for example, that one where you have Fe3, PO3, 2. So let's talk about that one. So iron, copper, lead, those are the manganese. Those are the ones that are most commonly used in terms of having an identity crisis in terms of which oxidation number they are. Especially manganese. Manganese can go all the way from 2+ all the way up to 7+. We're going to spend a lot of time talking about manganese when we get into the redox unit. So here's the difference. If I go to Gracie and I say, hey, Gracie, I need you to go get me a bottle of aluminum chloride. Aluminum chloride can only exist as AlCl3. Okay, that's it. It can only exist in that ratio. But if I say, hey, Gracie, I need you to go to get iron, a bottle of iron chloride. Gracie's going to go, whoa, Mr. Burkamp, which one do you want to get? Because iron can exist as 2 possible oxidation numbers. It can exist as iron 2+, and it can exist as iron 3+. So Gracie's got to ask me for that clarification, because there's more than 1 possible oxidation state. I'm not going to put Al3 chloride. There's no need. Because chlorine is only 1-, aluminum is only 3+. So this is why I don't put a Roman numeral when I name aluminum chloride. because it can only be AlCl3. Iron, copper, lead, manganese, those have more than one oxidation event, so you have to figure that out. So here's the simplest thing. Do that reverse stop, cross step, put that 2 up there, and move that 3 up there, okay? Your anions never have more than one oxidation state, okay? That's it, they never have more than one oxidation state. It's only your cations, and it's only certain cations that have more than one oxidation state. So here's the most common mistake that's made. You name that iron 3 phosphate, okay? That's wrong on 2 accounts. Why is that wrong?
It's phosphite.
Phosphite, because it's PO3, right? You have ites and you have eights. Those relate to the number of oxygens. Eights always have more oxygens than the ites do, okay? Like phosphite is PO3, phosphate is PO4. Sulfite is SO3, sulfate is SO4. So eights always have more oxygens than ites. Nitrite is NO2, nitrate is NO3. Does the 3 indicate how many atoms there are, or does it indicate the oxidation state? The oxidation state. So that's why this needs to be iron 2 phosphite, okay? The 3 does not, that Roman numeral tells you the oxidation state. It does not tell you how many atoms there are, okay? Cool with those. Okay. So on number 2, 2 of those should have Roman numerals, okay? 2 of them should have Roman numerals. When you get to number 3, your percent composition, so if you get the first one right, I figured the rest of them were right. So on that sodium hydrogen carbonate, your percentage of sodium should be around 27, okay? Something like that. And on number 3 with that manganese dichromate, that percentage of that manganese should be around 15. Okay, so at least gives you ballpark. On number 4, the moles of strontium hydroxide into grams. Make sure that you remember that strontium hydroxide is SrOH2. Okay, when you're figuring out that molar mass, it is just don't do, oh, it's strontium hydroxide, it's SrOH. It's not SrOH. Strontium is 2+, hydroxide is 1-. You have to have 2 hydroxide groups. So your answer, that first one with the moles of strontium hydroxide into grams, that should be around 30 grams. And that cobalt chlorite, those number of moles should be around 0.2. So both your answers on number 4 should start, or should be, that first one should be around 30. The second one should be around 0.2. Okay, it's an ish. On 5, where you're balancing those equations, every one of those balanced equations should have a coefficient of 3 somewhere.
Can you explain like decomp synthesis, single replacement, and double replacement?
Yeah. Okay. So let's start with like potassium chlorate. This is one of my favorite decomposition reactions. And this is part of a bigger idea, okay? So one of the things that we're going to spend a lot of time talking about in chemistry is basically chemistry boils down to the study of 2 things. At the end of the day, it's 2 things. You're either forming bonds or you're breaking bonds. That's it, okay? That's it. So if you have potassium chlorate, it's a white powder, okay? Looks like flour. And you have an ionic compound, it's potassium chlorate. And at the end of the day, the only thing that this can do is decompose because it's not reacting with anything else. So you can always recognize decomposition reactions because you start with one compound, okay? Now, decomposition reactions generally follow certain rules, like chlorates, when they decompose into metallic chlorides and oxygen. So out of this, you get KCl and oxygen gas, okay? I don't expect you to know that, but here's how you can always check that decomposition produces oxygen gas. Because if you have oxygen gas produced, and if you put a burning wood splint in it, the burning wood splint glows brighter. Okay, so there's 3 tests you can do with burning wood splints. If you put a burning wood splint into a test tube and it glows brighter, that's because there's oxygen being produced. If you take a burning wood splint and you put it into a test tube and it makes a popping sound, that's the presence of hydrogen. Okay? If the flame goes out, that's an indication that there's carbon dioxide. So that's how you can check for the presence of a gas. If the flame goes out, it's carbon dioxide. If it glows brighter, it's oxygen. If it makes a popping sound, it's hydrogen. So decomposition reactions, you're going to take the compound and you're going to break it up into 2 different things. Synthesis reactions are basically the reverse of decomposition reactions. So if you want to make water, you're going to take hydrogen, react it with oxygen, and you're going to make water. So synthesis reactions are the reverse of decomposition reactions. Now, here's the deal. Potassium chloride. If you're going to do this reaction, you have to heat it up, because you have to put energy into it because you're breaking bonds. And this is one of the recurring things you're going to see again and again and again and again and again. If you break bonds, like for example, you have hydrogen, and if you want to separate those, you have to put energy into it. When bonds are formed, energy is released, okay? So if you look at taking potassium chloride, if I gave that to Leslie and I said, hey, I need you to do this decomposition reaction, right away she's going to go, okay, I got to break bonds. The only way I can break bonds is if I put energy into the system, or put energy in because I have to pull apart these atoms that are stuck together. It's the same way with ice, okay? If I gave you a chunk of ice and said to melt it, what would you do? Would you put energy in to melt the ice, or would you take energy out? You put energy in. So whenever you break bonds, like melting ice, you put energy into the system. When you form bonds, energy is released, okay? So if you look at the combustion process of gasoline in your engine, okay? It works because of the fact that you have octane, which is a very unstable compound. You throw in an ignition source, it explodes, okay? It's a controlled explosion. And then you get carbon dioxide and water vapor out of a combustion reaction. Well, when you form those, so you have to put energy in to break the bonds, that's why you have to have a spark plug. It breaks those bonds and then it reforms carbon dioxide and water. So in the formation of those new bonds, you release a tremendous amount of energy. This is why we burn natural gas. This is why on a Bunsen burner, okay, hey, we're burning natural gas, because in that process, and you're forming new bonds, you release a tremendous amount of energy, okay? So when you form bonds, energy is released. When you break bonds, you put energy in. And that determines if the reaction gives off heat or if it takes in heat. So you all have seen an explosion of a hydrogen balloon, right? Everyone's seen that. Everyone has seen this, right? Well, let's see. Hold on. Let's blow one on that.
That's where it makes a loud sound.
Yeah, in the case of the fire.
Nothing like a good explosion to start off.
He's like, are you sure? Sure has no one seen it?
I'm really cold.
Wait, what?
I have no memory. He loves doing it, so he's happy. He's done it so many times. I swear I must be.
Yay!
I have no memory of it. Lisa has no memory.
She did not. Stand on the table.
Yeah, sit on the chair.
Work him. She let it go.
You had one job. You had one job. That's why I told you to hold it. The hydrogen is lighter than air. Okay, let me go get something to ignite it with. I'll be right back.
All of a sudden, I come off. I have no memory. So it's getting broken apart. Just like
She demoed the potassium permanganate. That's it. I kind of miss her. So we were
I had to make solutions for pictures.
You did?
It just stressed me, dude. I was like,
I don't know. No, the fact that like I don't know if it.
I don't know if you like add this
at least I have Elizabeth Trantham with me. She knew it.
Isn't she the one that's twins?
Yeah, she's like curly hair, really like really curly hair, like glasses. Right? She's really girl, like really.
She was in my athletic training class. What is it? Athletes care or care of athletes.
Yeah.
I hate my English class so much, bro. It's like actually the worst.
I think mine was pretty solid. And she goes,
Guys, do you think they let me switch into AP?
You do not want to switch into AP.
Ask Fry.
Do you really?
You didn't do any of the work.
Ask Fry. You should.
I just want to be with my friends, you know?
In AP Lit.
Yeah! But like, not the worst.
I know what I like when people like this. They're all like, I hate everyone.
You hate everyone in there?
Ours is funny. Everyone.
I was like, okay. I thought I liked everyone in there, but maybe not.
So Leslie's English class was Leslie.
Yes.
screaming at Dalton. Dalton dropping off.
Do you guys actually talk in there because
Yeah,
no one talks?
Wait, if you can't talk, then no, I don't want to be in there.
Yeah, I talk all the time in class.
See, I just want that. I just I feel like
It's like AP Gov.
But like, you do work.
Yeah, don't you guys have a lot of work? So bad.
Not yet.
Don't you ever study my candle?
I don't know
These
how.
regular English classes have a lot of work.
I don't think I could handle it, to be honest.
I know.
Okay, so. Get that up.
And then you better
So. Alright,
I'm so scared.
you got this. You ready?
It's fine. Boom. Oh my god!
Okay.
Nothing's really good.
Yeah.
That was awesome. I miss it. We will do it.
Okay. So, here's the deal. So, what that just showed is that we took hydrogen and oxygen and we recombined them into making water. So, in that process, you all felt that heat. You heard it, okay? So, it was like a roller coaster. So, the hydrogen and oxygen were here. I lit it on fire, it went up the roller coaster, and then we ended up down here, and we made a little bit of water. Okay, not enough to make it rain inside the classroom, but we made a little bit of water. So, because there was so much energy given off, there was an exothermic reaction. So we formed these new bonds that make up water, and it's like a roller coaster. When people go down a roller coaster, they go, wah! Okay, right? Okay. That's what happened on an atomic level. They went down the roller coaster. Now, if I want to reverse the process, if I want to take water and separate it into hydrogen and oxygen, I have to push it up the roller coaster. So I would have to put energy into it to separate it back out into hydrogen and oxygen, because then it would be breaking bonds. So that's the short version. Okay? Decomposition, you break them apart. Synthesis, you combine them. On a single displacement reaction, So for example, you look at the one where you have aluminum and sulfuric acid. You can always recognize single displacement reactions, also known as redox reactions, because you have a single element reacting with a compound. So if you look on that, let me see somebody's colorful periodic table, not periodic table, but that. So on the back side of this, you'll notice that aluminum is up here and it's above hydrogen. So that means is that aluminum is more reactive than hydrogen is. So this is going to lead into a discussion of redox. This is one of the questions. So on a redox reaction, here's the easiest, well, there's different versions of this, but I always like, because I spent time in Africa, I always like to say Leo says girl, okay? So if you lose electrons, that's oxidation. If you gain electrons, that's reduction. So basically what happens is this. The aluminum comes along and it has all of its ions, okay? It's all of its electrons, excuse me. It's a neutral atom. It's a chunk of aluminum like this, okay? So when you have the elemental form of a substance, the oxidation state is 0. Okay, it hasn't lost electrons, it hasn't gained electrons. Just aluminum, that's it, it's just aluminum. So what's going to happen is that I'm going to drop that into the sulfuric acid. Now, this is going to be part of a bigger discussion. Sulfuric acid is what's known as a strong acid. Strong acid means that in the solution, you have hydronium ions off by itself, and then you have the sulfate over there, okay? If something is a strong acid, it's said to completely ionize, which means the hydronium ions go off and the anions go off over here. They're ionized, they're separated. So basically what happens is this. This hydrogen ion, and we're going to spend a lot of time talking about hydronium ions, which is basically nothing more than a single proton. So a hydronium ion is a proton, that's all it is. So this proton comes along to the aluminum and says, yo, so, mind if I take some of your electrons? Now, the aluminum is in a quandary at this point. It's a moral quandary. Aluminum is formed in the death of stars. Okay? So these aluminum atoms have been together for a long time. I mean, they were formed in deaths of stars. They got kicked out into the universe. Okay? We reformed here in Earth, and then they got mined, and then they got processed, and they got rolled, and they're stuck together. So these aluminum atoms have been together for a long time, okay? And they've had these electrons for a long time. And so the hydrogen comes along and says, so, mind if we dance with your electron? And the aluminum says, screw it, take them, I don't care, okay? Because aluminum is going to end up more stable. So the aluminum gives away these electrons. And these electrons have been together for a long time, okay? These were formed in stars. They got rolled into foil. They've been together for a long time, and the aluminum says, whatever, take them, I don't care. A pain, okay? So the electrons that were with the aluminum, they go over and they bond with the hydrogen, because they give this up. So this is how you can always recognize a single displacement reaction, because you're going to have one element. So if you look at this, the aluminum comes along, it kicks out the hydrogen, and then the hydrogen gas is formed because hydrogen is a diatomic, and that's why it's H2. So what you would see happening in this reaction is that you would take this piece of aluminum, you would drop it in sulfuric acid. You would see the aluminum dissolve because it's forming ions. And you would see bubbles of hydrogen gas forming. Okay? So that's how you can recognize single displacement. Now, double displacement. Double displacements are all of these going to be like on question number 6 on the back side. So let me show you a simple double displacement reaction. So here I have sodium hydroxide. Okay? Come on. A little more than that. Sodium hydroxide. So sodium hydroxide is a base, okay? Because it has hydroxides on it. And then to that, I'm going to add a little bit of magnesium nitrate. So it's important that you understand what this looks like on an atomic level. Sodium hydroxide is soluble because it's a group 1 element. So it's important that you visualize what this looks like if you could look at the atomic level of this reaction. So here's a water molecule, okay? You got the hydrogens, there's your oxygen, right? And this hydrogen up here, then you got the oxygen down here, okay? So the hydrogen end of the water molecule is positively charged because it's taking its electrons and it's giving it to the oxygen. The oxygen is negatively charged, okay? Because it's taking in those electrons. So the oxygen end of the water molecule is negatively charged. The hydrogen end is positively charged. That's why it makes it such a good solvent, because you have positive and negatively charged ends of the water molecule. So if this is Wally the water molecule, so you have a negative end down here, and you have a positive end up here. So the sodium hydroxide, okay, here, basically what happens is that sodium hydroxide, if you were to mix this up, you would take sodium hydroxide pellets, so white powder, and you would dissolve that in water. So this is a tug of war. So what happens is that the sodium is attracted to the hydroxide. They're oppositely charged. Cool. I like you. Sodium hydroxide. But what happens is the sodium comes along, because the sodium is positively charged because it's lost an electron. So the sodium goes, oh, look, there's a negatively end of the charged water molecule. I'm positive, you're negative. Oh, it's like Romeo and Juliet on an atomic level. Okay, opposites attract. It's cool. Yeah. And the hydroxide goes, well, screw you too. You go to that end, I'm going to be attracted to the hydrogen end because that's positively charged. So this is a tug of war. So the sodium is attracted to the hydroxide, but it's also attracted to the water molecule. So the sodium and hydroxide are conflicted. They go, ooh, do I stay with the sodium? Do I stay with that? Or do I go bond with the water molecules? And they basically say, screw you, we're out. Okay? It dissolves, the sodium is attracted, the hydroxide is attracted to that end. So on an atomic level, what's happening is that these are attracted to the water molecules. We don't discuss the water molecules, but they're there. Now, the same thing has happened to magnesium nitrate. Magnesium nitrate, all nitrates are soluble. So here I have magnesium nitrate. So I'm going to put that in here. So I'm going to add some magnesium nitrate. Now, you notice as soon as I do this, we begin to form a precipitate. Okay? So basically what happens is this. You have sodium ions, you have hydroxide ions, you have magnesium ions, and you have nitrate ions. Okay? So this is like a dance. So the sodium runs into the magnesium. Are they going to be attracted to each other?
No.
No, why?
Both positive.
Both positively charged. Hydroxide and nope, not happening. But the sodium comes along to the nitrate and says, ooh, I like you. Okay? You're oppositely charged. But they're going to be attracted to each other. But are they going to form a precipitate? No, because all nitrates are soluble and all group 1 elements are soluble. You couldn't make a precipitate of sodium nitrate if you tried. Okay, this is like the model of solubility. But the magnesium comes up to the hydroxide and goes, ooh, I like you. Okay? Now, if you look on your solubility rules, okay, actually most hydroxides are insoluble, which means on a tug of war, the magnesium and the hydroxide form a tighter bond with each other than they did with the water molecules that they left behind. So now, this is like the reverse of something being soluble. So the bond between the magnesium and hydroxide is so strong that it leaves the water molecules, bam, they hook up together. They hook up together, and that's why you have a precipitate of magnesium hydroxide. So whenever you form a precipitate, it's because the bonds between the cations and the anions are stronger than they are for the water molecules. Okay? So that's how you recognize a double displacement reaction. So for example, when you get to number 6, that first one, you had sodium hydroxide and iron 3 nitrate, I want to make sure everybody's cool with what I want on that net ionic. So first off, your precipitate is going to be the FeOH3. Okay, that's going to be your precipitant. So what I want on that net ionic, and we're going to spend a lot of time talking about net ionic reactions. So what I want is that first off, you recognize that it's Fe3 plus. You should have 3 hydroxides, and that forms FeOH3. So that's what that net ionic equation should look like. Now, net ionic reactions, we're going to spend a lot of time talking about these. So listen to me very carefully. Net ionic reactions need to balance on 2 things. They need to balance on the number of particles, which is the law of conservation of mass, and they also need to balance on charge, because you have to have the law of conservation of charge. So if you just put Fe3OH, it's not balanced, because you would have 3 positive charges and only 1 negative charge, and that would add up to positive 2. Because there's no charge on the FeOH3 side. So by putting that 3 in there, you accomplish 2 things. You balance the number of hydroxide ions, and you balance the charge. Because now I have 3 positive charges and 3 negative charges. That adds up to equal to 0. And that FeOH3 is 0 on the other side. So on those net ionic equations, if you're not sure if you're right, count the number of particles on each side, count the charge on each side. If they're the same, you did it right, most likely. And if they're not, you're screwed. Okay? Yes?
On ones like the manganese chloride one, so chloride has a subscript of 3, right? On the net ionics, do you leave the subscript in the subscript, or do I move that to like before?
I don't know what you're asking.
Okay, so like, is it 3Cl, or is it still like Cl3, or does that matter?
It's 3CL.
Is it 3Cl?
On your net ionic,
Yeah.
everything is wrong.
Are they supposed to have nothing?
Yes.
Okay. Well, I didn't know if I had to leave.
No.
the 3.
Okay.
Okay.
Your precipitate is silver chloride, right?
Uh-huh.
What happens here has nothing to do with happened up above.
Okay, that's what I needed to know.
So this is just Ag plus CO minus.
Okay.
That's it.
I was
No,
thinking-
no, that's it.
Yep.
Yep. That's it.
Yep.
That's it. Good. Leslie?
Do you have a preference for whether the precipitate is expressed as an S or a PPT?
Either one.
Okay.
Or you could just put, some people just put like a down arrow.
Okay.
Yes,
And then for the normal equation, that's just your regular chemical equation,
but balanced.
but balanced.
Yes,
Okay.
yes. So, except for the AgCl, the other 2 net ionics should have coefficients in front of them. At least one coefficient. Okay? This is the only one that has the same oxidation states. Okay? Everybody cool with that? Okay. On number 7 with that stoic, I want to make sure everybody's cool with how I want this worked. So let's talk about B. How many grams of aluminum chloride could be produced from 1.08 grams of aluminum? Okay? So this is what I want to see. You're going to start with 1.08 grams of aluminum, right? So the first thing you have to do is convert the grams of aluminum into what? Moles of aluminum. Okay? So you look at that and go, okay, 27.0 grams of aluminum is 1 mole of aluminum. Now, if you stop right there, yes?
Do we have to draw it like how you're drawing it? Or
What's your other option?
like the railroad tracks? Like the times?
Like
draw
just
lines?
X. It's like
Yeah,
just
that's what I do.
like
Oh,
lines
that
in
just,
between.
that makes me confused.
It's the miss out way.
The miss out way.
It's like a.
KS.
It's like fraction times fraction times fraction.
Yes, that one.
Yeah.
I also like Miss Ut's way.
Like that?
That's the one. I just didn't know if you had like a preference.
Here's the story. How you do the artwork doesn't matter.
Okay.
Okay? Doesn't matter. But what's most important is that I see the units.
Okay.
Okay? That's the most
The
important.
units.
Because so help me God. If you do this, hold on, that's out of habit. If you just do this, 27, and then times, and there's no units, I will completely flip out. Okay?
I like this.
So if you want to do the cute little times thing, it's cool. But here's what's going to be most important. I want to see the units canceled out. Okay? What?
We can't read your writing.
It was all wrong anyway.
It's like, this is like consistent.
Okay.
This isn't really the only time
Yeah,
we can't read your writing.
when
So if you want to do,
then he kept switching to leave.
And you have to go.
if you want to do the little dots, times, that's cool. I always like to do the cells, okay? Just pick one. But so help me God, right? All things protons, electrons, and neutrons. If all I see is random numbers, bad things are going to happen, okay? I have a certain amount of time left on this earth. I am not going to waste my time sorting through random numbers that have no meaning, okay? What? Are we okay?
Yeah.
Okay, because you seem quite appalled by that statement. Okay, so if you stopped right now, what would you have? Moles of aluminum. Okay? So the first thing you're going to do is you're going to figure out how many moles of aluminum that you have. Then what do you have to do with the moles of aluminum? Convert those into moles of, in this case, well, we're doing B. Okay, aluminum chloride, right? So where are you going to look to find that information?
Your balance equation.
Balanced equation, okay? Stoichiometric calculations. So in this case, you're going to have 2 moles of aluminum to every 2 moles of aluminum chloride. So if you stop right now, what do you have? Moles of aluminum chloride, okay? It's cool. Now, but you ultimately, what do you want to end up in? Grams. So 1 mole of aluminum chloride, make sure you're using 35.5, which is 133.5 grams of aluminum chloride. Everything cancels out, you get grams. Boom, there you go. So this is what I expect to see, whether you use the UT way or the right way. So just as long as I can see what you have done. That's the most important thing, okay? Anyway, let's talk about 8B on that molarity, okay? Because on this one, on 8B, you've got sodium sulfate. So here's the deal. What do you think you have? What's the first thing you're going to have to do with that sodium sulfate? Let me give you a hint. Rhymes with the word formula.
Formula.
Yeah. So what's the formula for sodium sulfate? Na2SO4, right? So you've got the 24.8 grams of sodium sulfate. Yes, I'm going to do, because this is the way I've done this longer than you all have been on this earth. So you got 142.1 grams, 1 mole of sodium sulfate. Now, here's the deal. When this ionizes, okay, and it's going to ionize because of the fact that it's a group, sodium is in group 1, so that means it's soluble. It's going to dissolve. So if you kind of visualize this as being sodium sulfate, here's the sulfate, here's the 2 sodiums attached to it. This thing is going to ionize. So then, whoop, it's going to break apart like this. So how many sodium ions do you get out of every 1 sodium sulfate? 2. So when you do this, so that's 1 mole of sodium sulfate. But then for every 1 mole of sodium sulfate, you get 2 moles of sodium ions. Okay? Then your last step, because it asks for molarity, if you stop right now, what units do you have? Moles of sodium ions. You want molarity, so what's the last step that you have to do? Divide by liters, because you have to have moles per liter. So that answer on 8B for that molarity of your sodium ions would make an GPA. Not horrible, not bad, okay? Okay? And certainly seen a lot worse. 8C should be in the low 30s, and 8D should be very much less than 1.
She doesn't like how you give the answers out.
Yeah, get
At least
used
does
to
it. It's the
it.
bird camp life.
You'll begin to pick that up, okay?
We'll figure it out.
You'll figure it out. So which one would you like more clarification on?
I like the answer.
Nope, not happening. Nope,
Great.
nope. Be thankful I'm at least giving you an ish kind of thing, okay? Yeah, let's go with that. Now, let's talk about number 9, acids and bases. So, again, I'm just going to assume that I'm kind of starting from scratch. So, you typically have a pH scale which goes from 0 to 14. 7.00. Because I want to spend some time on this because this is going to be our first big unit is on acid bases. So I want to make sure everybody's cool with this. So on your equation sheet, you have a couple of equations. You have pH equals negative log of your hydronium ion concentration. You have POH, which equals the negative log of your hydroxide ion concentration. You have pH plus POH equals 14.00. And you have Ka times Kb, I think this is on there, equals 1.0 times 10 to the negative 14. Okay? Yeah, something like that. Here's the main point. When you see P in front of anything, pH, POH, pKa, pKb, letter P stands for the negative log. Okay, so when you see P, that means it's the negative log of whatever follows that. Okay, so if it's POH, it's the negative log of your hydroxide ion concentration. If it's your pH, it's your negative log of your hydroniums. Okay, eventually we're going to get into this concept of Ka and Kb. So if you see pKa, that's the negative log of a Ka value. Okay, so all you have to remember. So if something is neutral, it has a pH of 7. So what that means is that the only way you have a pH of 7 is if you take the negative log of 1.00 times 10 to the negative 7th, you get 7. So neutral water has a pH of 7 only because in neutral solutions, the hydronium ion concentration is 1.00 times 10 to the negative 7th. You take the negative log of that if you get 7. If neutral solutions had a concentration of 1.00 times 10 to the negative 8th, neutral solutions would have a pH of 8. If it was 4, it'd be 1 times 10 to the negative 4th. So the only reason it has a pH of 7 is because if you take the negative log of 1.00 times 10 to the negative 7th, you get 7. That's why it's that number, okay? So here's the other important thing, is that when you take your hydronium ion concentration times your hydroxide ion concentration, you get 1.0 times 10 to the negative 14. 1.0 times 10 to the negative 14 is what's known as the autoionization constant of water. And it's specific at a certain temperature of 25 degrees Celsius. So unless you're told anything different, you always assume that those two numbers multiplied together equal 1.0 times 10 to the negative 14. So when you have a neutral solution, the reason that it's that is because if you take 1 times 10 to the negative 7 times 1 times 10 to the negative 7th. Oddly enough, you get 1.0 times 10 to the negative 14th. If in a neutral solution, if those were both 10 to the negative 8th, the auto ionization constant of water would be 1 times 10 to the negative 16th. Okay? So there's nothing magic about it. Mother Nature said, for whatever reason, that's where we're at. Okay? That's the hand that we're dealt. Okay? 7, 14, boom, there you go. So there's a couple of things to keep in mind. This number doesn't change. So when you multiply these two numbers together, it always equals 1.0 times 10 to the negative 14. So what that means is that as your hydronium ion concentration goes up, your hydroxide ion concentration has to go down. Because when you multiply them together, you always have to equal 1.0 times 10 to the negative 14th. Okay? So they're inverses of each other. So as one number goes up, the other one has to go down. Because the multiplied together always has to equal 1.0 times 10 to the negative 14th. Now, don't ever tell me, oh, that's water. 1.0 times 10 to the negative 14th is not water, okay? It's the auto ionization constant of water, but it's not water. Okay, it's just a number. So, when you get to number 9, okay, that first question, what is the pH of a 0.015 molar solution of hydrochloric acid? So here's what's going to be important about this. If you have not begun to memorize the strong acids, okay, you need to do that because that first quiz on Wednesday, you have to know 4 of them. Hydrochloric acid is like the poster child. So here's a quick way to learn most of the strong acids. If you notice on the strong acids, a lot of them are halogens like fluorine, chlorine, bromine. The only one of your halogens that is not a strong acid is fluorine, okay? All the other ones, hydrochloric, hydrobromic, hydroiodic, those are all strong acids. So if you're on the test and you're going, oh man, God, oh, don't know my strong acids. Find the halogens, okay? Except for fluorine, they're all strong acids. Oh, hydrochloric, hydrobromic, hydroiodic, okay? There you go. There's 3 of them right there, okay? Easy. So this is a bigger discussion. Hydrochloric acid is a strong acid. So what that means is that strong acids completely ionize, which means they completely separate out. So again, water molecules are going to be an important part of this story. So here's a water molecule. And you have your negative end and you have your positive end. So basically, again, this is a tug of war. So the HCl, the hydrogen and the chlorine, okay, they're oppositely charged, so they're attracted to each other. The hydrogen and chlorine, it's cool. Hydrochloric acid, we're buds, that's why we call it, right? Hydrochloric acid. So here comes this water molecule, okay? The hydrogen and chlorine basically says, you know, I was attracted to you, but we're just friends, I'm out. I'm gonna go hang out with the water molecule. So this hydrogen comes along and it goes, woo! I'm gonna be attracted to the oxygen end because that's negatively charged. The chlorine says, well, fine. I'm gonna be attracted to the positive end of the water molecule. This is a tug of war. So here's the best analogy I give. Prom's going to be coming up before too long. This is like you and your date show up at prom, and you're just friends. Okay, you're together, but you're not together. If that makes sense, right? And then you get to the prom and you go, wow, there are some other people. I'm going to hang out with the other people. Okay, we're just not that into each other. So you exist long enough to get to prom. But as soon as you get to prom, you separate out, okay? So strong acids, and here's the dichotomy. Strong acids have exceptionally weak bonds between the proton and the anion, okay? They're together, it's a really, really weak bond. So that's the dichotomy. Strong acids have really, really, really weak bonds between the acid itself, okay? So what happens, because this is a strong acid, and we're going to talk about Rice charts a lot. So let me kind of briefly introduce the Rice chart. So on the Rice chart, the R stands for the reaction. So what's happening in here is that you have hydrochloric acid, and I'm going to write out the kind of big formal one. And I'm going to include water in this. So what's going to happen is that you're going to form H3O plus Cl minus. Right? So a couple of things about the language of chemistry. H plus, when you see the square brackets, anything written in square brackets refers to concentration measured in molarity. So when you see H plus in brackets, that's indicating that we need to talk about the concentration of hydronium ions measured in moles per liter. H3O plus means the exact same thing. So H plus and H3O plus are both indicate hydronium ions. The H3O plus is technically more correct because it shows it bonded to a water molecule. This is technically, on an atomic level, what's happening. But chemists are basically lazy, so most of the time we just put H plus, okay? Technically, H3O plus is more correct. But typically, we just talk about the concentration of the hydronium ions. So, when you see a Rice chart, the R stands for the reaction. And if you don't know what the reaction is, nothing else is going to make any sense later on. So here's my reaction. So my initial conditions were 0.015. That was my initial concentration of my molarity. I assume that I have no hydronium ions, and I assume that I have no chloride ions, okay? Nothing's there. You show up to the date, with your date to the prom. You're together. You haven't ionized, okay? You're with your date, okay? Now, the change is going to be what's going to happen. So because this is a strong acid, all of this is going to go away. It's always going to ionize. Any strong acid is completely going to ionize. It's going to go away. It's going to go. So this is going to go to 0. Okay? So I stands for the initial, C is your change, and E is going to be your equilibrium. So it goes reaction, initial, change, equilibrium. And Mother Nature is all about the equilibrium line. Okay? That's what she's after. So this is going to be 0.015. This is going to be 0.015 because it's going to completely ionize. So what's going to happen is that now my hydronium ion concentration is 0.015. So when I get that pH, I'm going to take the negative log of 0.015 because that becomes my hydronium ion concentration. When you get to that one where I give you the pH, it's just the opposite. You have a pH of 4.57. So to figure out the hydronium ion, you undo the negative log. So you take negative 4.57. So you're going to take 10 to the negative 4.57, and that's how you're going to get your hydronium ion concentration. Okay? What time do you all bug out? 105? 105? Okay.
Wait, can you go?
Now, can I what?
Can you go back through that again?
Okay.
Math?
So on your Rice chart, R stands for the reaction. I is going to be your initial set of conditions. C is what happens when you change. And then E is your equilibrium line. Okay? So in this situation, you go 0 plus 0.015 plus 0.015 equals 0.015. Now, in contrast to that, over here on this last page where you have weak acid calculations, it's the exact same idea. But on this one, you're going to be talking about acetic acid. We're going to spend a lot of time talking about acetic acid because acetic acid is really cheap. Acetic acid is just basically vinegar. So on number 12, I kind of lay this out, and here's the Rice chart, right? So I get you started. So the reaction is going to be your acetic acid, HC2H3O2. You talk about the water being in there. You're going to form hydronium ions and C2H3O2 minus. Okay? So basically the water comes along and it says, hey, we're going to take some of your hydronium ions. Now, acetic acid is a weak acid, which means that it doesn't ionize completely. So we'll take this up on Monday. So this is where we'll take off on Monday. Okay? No homework. Other than finishing this up. That's it. That's it.